couple public service announcements. One is Zoom has decided that we need to have passwords. And so starting on the 27th, we're going to have to, I'll probably do it before then, but just watch out because there's going to be a new Zoom link and there'll be a password and it'll be something easy like chemistry, and that'll be stated on the homepage. So this Zoom code and this link are not going to be good in a couple days because Zoom has decided that everybody needs to change their links if they don't have passwords. So this information will change, and I'll probably, when I change it, put it in a different color just so you recognize, oh, that's different. So if you go to a meeting and we're not there, that might be why. And then today we're starting a different topic. This week is ions, ionic compounds, and weighted averages. And so I have some Zoom notes here. This is a PDF that you could write on if you wanted to as I go through the presentation today. And then this is GoodNotes. So if you have GoodNotes, which is an app, maybe for an iPad, you could write right on your iPad with those notes. Okay, so I'm gonna go ahead and show you some things I have for you. Still letting the people in. Okay. So, you know, you can go through at the bottom where it says next and previous, but I'm just going to go to modules and look at week 5, which is the week that we're in. Periodicity has to do with the periodic table and some patterns that are there. And then weighted averages is the other topic this week. So I'm going to go down to ions and ionic compounds. And so there's a video you can watch that'll be very similar to the Zoom that I'm doing today, but you probably should still watch it. And remember that you can watch it at a faster speed, so you don't have to watch everything slowly. You can speed it up and you can skip things. And then here's a packet. This packet is pretty important. We're going to be studying nomenclature, which is the system of naming things. And we're going to be doing this for 2 weeks. Well, we're going to be doing nomenclature all semester. So you know how sig figs kind of never go away? Nomenclature is like that. So here I've got the doc. And I'm going to talk through this first 6 pages today. It's going to talk about how to name things, and then how to put ions together and how to name them. And then here is a key. So page 3 is a key to page 2. Here's a little more information about transition metals. Here's a practice grid. We're up here, and I'll model this today in Zoom. Up here, you would make the ionic compound, and down here, you'd write a name for it. And then there's the key. So the answers are on the subsequent pages. Nomenclature is one of those things. And then when we get here to polyatomics, which is page 7, these are things that you'll need to memorize. I'm not going to talk about them today, but you might want to make flashcards. And then another page and a key. Monatomic ions and ionic compounds is the topic for today. A monatomic ion is just a 1 atom charged particle. And so sodium, for example, can be sodium the metal, or it can be sodium the ion. Sulfur can be sulfur the nonmetal, or sulfide the ion. These ones are monatomic, which means 1 capital, 1 atom. 1 atom has lost an electron and become positive. If you lose something negative, you become more positive. 1 atom has gained 2 electrons, and electrons are negative, so it's more negative than positive by 2 electrons. So monatomic does not mean polyatomic, the opposite of that. And polyatomic means many atom chunks that have gained or lost electrons. And so we could have polyatomic ions that are positive. This one is called ammonium ion. You need to make a flashcard and memorize that. We could have polyatomic ions that are negative. This one is called sulfate. It's one of the anchors that you need to memorize once you know sulfate and how to use the periodic table. You can come up with a lot of other anions. And sometimes polyatomic doesn't mean poly. You know, it's too many. But if it's more than 1, if it's not monatomic, it's polyatomic. And this ion is called hydroxide. So we're just dipping our toes into nomenclature, and we're going to talk about how to use the periodic table to make predictions so that not everything is being memorized. It would be a huge burden if you had to memorize 300 names to go with formulas that you see. But if you understand the periodicity on the periodic table, then you save yourself a lot of time. Okay, so metals lose electrons to form cations. You are familiar with this line. This stair-step line separates metals from nonmetals. And the nonmetals would be the things to the right of the line. Except for hydrogen. Hydrogen is a nonmetal, even though it's on the left of the line. And then metals would be most of the elements on the periodic table. There are some elements that are called metalloids. So for the elements that are touching that stair-step line, except for one, those are semimetals or metalloids, and those two words mean the same thing. The one that is not a semimetal or a metalloid is aluminum. It is a metal. Okay, so most of the elements are metals, and metals lose electrons to become more stable. To become more stable just means physically more stable. Like if you had a precious glass vase and a cat, would it make sense, you know, to put that expensive thing, you prized possession, here's my vase. Look how lovely it is. On top of a high thing, put some water in there, add some flowers. No, because you have a cat, and even though it is stable up there in that surface, if it got just batted by a cat, it would be knocked off. So it is stable on that maybe bookshelf, but it would be more stable on the ground. Why? Because it's lower in potential energy. Potential energy has a formula in physics, mgh. M stands for mass, H is the distance it could change. So from up here to down here would be my H, and then G is the force of gravity. So even though an atom, a metal atom can exist, like the vase up high here, it would be more stable if it had a different arrangement. And that's what we're talking about, how metal atoms become more stable by losing electrons. And when metals lose electrons, they form cations. A cation is a positively charged atom or chunk of atoms. So here's sodium. Sodium is element number 11. And there are different isotopes of sodium. So there would be a mass number that could go up there. But if it's sodium atom, it has 11 protons, which are positive, a plus 11 charge in the nucleus. Some neutrons, depends on the isotope, but neutrons are neutral. And then if it's an atom, the net charge is 0. So if there's 11 protons, we need 11 electrons to balance that. So if the overall charge is 0, that's an atom. But metals lose electrons, and sodium typically loses 1 electron. So now I'm going to talk about sodium, the ion. Sodium still has 11 protons, or it wouldn't be sodium. It has some neutrons, depends on the isotope, but neutrons are neutral. But if it could lose 1 electron and only have 10, it would only have a negative 10 charge. Oops. A negative 10 charge outside the nucleus and a plus 11 charge inside the nucleus. So the overall charge is plus 1. And so we're going to put this overall charge here, and now we have sodium ion. A lot of times we don't say the 11. we just say there's sodium atom. It's an atom that is a metal. And there's sodium ion with a +1 charge. Why does that happen? And the answer is because there's really something special about having 10 electrons. Noble gases are super stable. And the reason they're stable is because the number of electrons they have are sort of perfect numbers. And that has to do with electron configurations, which we'll talk about in a different chapter. But for now, all we need to know is there's something really special about 2, 10, 18, 36, 54, and even 86 electrons. So when sodium has the opportunity to lose electrons, how many does it lose? The same amount, so that it is isoelectronic with the nearest noble gas. And isoelectronic just means same number and arrangement of electrons. And today we're just focusing on the same number of electrons. The arrangement has to do with that idea of electron configuration that we'll talk about at another time. Okay, so metals lose electrons to form cations. Nonmetals gain electrons to form anions. So fluorine could be an example of a nonmetal. Oops. Fluorine is not stable like that. That is the symbol that we find on the periodic table, but that is not how fluorine exists in nature because it's not stable with 9 electrons. Fluorine, the atom, has 9 protons, or it wouldn't be fluorine. Some neutrons, turns out there's only 1 stable isotope. And then the atom has 9 electrons. So for the atom, the net charge is 0, but that's not stable. So fluorine as a nonmetal can either share electrons to be isoelectronic with a noble gas, to be more stable. And when it does that, we call those covalent compounds. Or it can gain electrons to become isoelectronic with a noble gas. Which noble gas? The one that it's next to. So here's fluorine in group 7, not stable. When it becomes stable by gaining electrons, it gains 1 electron. And then we call it fluoride. So for anions, when the atom gains electrons to become stable and isoelectronic with a noble gas, the name changes and there is the "ide" ending. 9 protons in the nucleus. Some neutrons in the nucleus. Outside the nucleus, fluoride ion has 10 electrons. And if you have more electrons than protons, that's a negative number. And so this is the charge on fluoride. The way we find fluorine in nature, if it isn't ionic, is something covalent. And often the element is like this. This is fluorine as the element exists in nature. Fluoride is more stable. And then sometimes fluorine can share with things that aren't other fluorines. And so we come up with a compound, which we're not going to talk about covalent compounds until next week. Okay, so on the periodic table, we have a symbol. And then in reality, we have formulas. So the formula for fluorine, the element, is F2, and the formula for fluoride is F-. Okay, so when sodium lost an electron to become an ion, its name did change. Before, we had sodium, and after becoming more stable, we had sodium ion. So sodium ion and sodium are very different. And when you watch the videos this week in the module, you'll see that sodium, which is an alkali metal, is so unstable that it reacts violently with water, forming hydrogen gas and often catching on fire. So when the doctor says you got too much sodium in your diet, the doctor is not referring to actual sodium. The doctor refers to sodium ion, which is a stable way sodium exists in your body. Okay, so when we're talking about this idea of metals lose electrons, nonmetals gain electrons, can we predict how many? The answer is yes, when we're talking about main group elements. So another way to look at the periodic table is to recognize column 1, column 2, and then columns 3 through 8. Those are all called representative elements. They are also known as main group elements. If it wasn't a main group element, what might it be? And the answer is a transition metal. These are transition metals. And then right here, in order to keep the periodic table fitting nicely on an 8.5 by 11 page that is landscape, instead of writing them in here, we write them down here. So these 28 elements all really fit right here. It's just we would have to cut our periodic table in half and stretch it. And so these are sometimes called the inner transition metals. They are also transition metals, but they're the ones within the larger group of transition metals. And they have some other names. This row here is called the lanthanides because it follows lanthanum. This row here is called the actinides because it follows actinium. That's its correct place on the periodic table. Okay, so for the thing we're talking about today, which is how many electrons are gained or lost, we can only know that based on position on the periodic table for the main group elements. And if it's a metal, it loses electrons to be like the previous noble gas. And if it's a nonmetal, it gains electrons to be by the noble gas that's coming up. So for example, here's aluminum. Aluminum is a metal, metals lose electrons. Aluminum is element 13. What is the previous noble gas? Neon. Aluminum, the atom, would have 13 protons, some neutrons, depending on the isotope, 13 electrons, the atom. But when aluminum becomes stable, it does so by losing 3 electrons. Why 3? Because it's in group 3. It's a metal in group 3, so it loses 3 electrons. It still has protons and neutrons. 13 minus 10 is 3. So aluminum, the ion, has a +3 charge. Metals in group 3 lose 3 electrons to become isoelectronic with the nearest noble gas. Gallium, indium, thallium, rubidium are all going to lose electrons to be like the previous noble gas, and will have a +3 charge. They don't have to be that way. They can be elemental or metallic. They can be an atom, or they can lose electrons and be cations with a +3 charge. So everything in group 1, remember hydrogen is not a metal, everything in group 1 can lose 1 electron to be like the previous noble gas, which is a more stable arrangement. Things in group 2 lose 2, and metals in group 3 lose 3. Nonmetals, here are my nonmetals. Nonmetals gain electrons. How many electrons? Well, how many do I need? If it's oxygen, oxygen needs to gain 2 electrons to be like the next noble gas. So here's oxygen, the atom. Here's oxygen, the element, as we find it in nature, O2. And then here's oxide. Oxygen is element number 8. It has 8 protons. Some neutrons, there are 3 isotopes, but neutrons are neutral. If it gains 2 electrons, it now has 10 electrons with a -10 charge. The overall charge is -2. So that is the charge on oxide ion. For phosphorus to become more stable, how many electrons would it need to gain? Phosphorus is element 15. When phosphorus becomes more stable by becoming phosphide, what charge does it have? When bromine becomes more stable, and we call it bromide, how many electrons does bromine need to gain? Bromine is element number 35.
Would that be 1?
Yeah. So if bromine gains 1 electron, it becomes bromide ion. And a lot of times we just say bromide. For sodium ion, we have to say sodium ion, because if we just say sodium, we're actually talking about something different. Because for anions, the name changes, sometimes we just say bromide. Okay, so it's super important that you understand that. There is a video and there are practice worksheets. So now I'm going to show you a grid that is an example of how to put these things together to make compounds. So an element is 1 capital, no charge showing. And so right now I just want to remind us what elements are. Sodium is an element. Carbon is an element. Oxygen is an element. Phosphorus is an element. These are elements because there's 1 capital, no charge showing. Now it's a little strange, you know, what's with that 2? And the answer is there are 7 elements that are not stable as atoms, so they exist diatomically. And the 7 diatomic elements are, and yes, this is a list you need to make and know. Are hydrogen, nitrogen, oxygen, chlorine, bromine, and iodine. There are some ways to remember this. There's 2 mnemonics, and then there's the placement on the periodic table. So I'll show you the placement first. So the 7 diatomic elements are, let's move hydrogen over here where it sometimes belongs. If I imagine this hydrogen hanging out with the nonmetals, this is its second home. And if I look at the 7 elements, starting at 7, seven is nitrogen. They make a 7. Kind of a funky looking 7, but you can see it, right? Those elements exist diatomically. So the nitrogen in the air we're breathing is N2. Oxygen in the air, which is a component of air that's important to us, O2. These elements are diatomic, and we need to know that. The other way you can remember it is a mnemonic device that goes like this. Horses need oats for clear brown eyes. Or a different way to do that is, have no fear of ice cold beer. Anyway, you need to know the 7. There are 3 elements that in our class that exist in groups of more than 1 or 2. So they're not monatomic or diatomic, they're polyatomic. And in our class, they are phosphorus, ozone, and sulfur. And a student once came up with this mnemonic: poor old Superman. Poor has 4 letters, old has 3 letters. Guess how many letters Superman has?
8.
Yes. So you need to know those. Poor old Superman, those are polyatomic. But the point here is an element just has 1 capital and no charge showing. Compounds have more than 1 capital and no charge showing. So a compound could be a compound made of nonmetals only, like carbon dioxide. And if it is only nonmetals or metalloids, but no metals, we call that a covalent compound. And covalent has to do with electrons are being shared. If the compound contains a metal that's become a cation and a nonmetal that's become an anion, so this is metal plus nonmetal, then we call that ionic because it's made from ions. So there are 2 kinds of compounds, covalent and ionic. And this week we're focusing on ionic, and next week we'll look at covalent. Okay, so when you see something like this, that's not a compound. Why is that not a compound? So some of you might be thinking, it's not a compound because there's a charge showing. A compound is more than 1 capital. So more than 1 kind of element. No charge showing. Okay, and now we're ready to put together some ionic compounds, which is the goal of today. So I have used the periodic table to come up with the formula for sodium ion, barium ion, and aluminum ion, fluoride, sulfide, and nitride. So these are the ions that we're going to combine in a way that we have no charge left over, no charge showing. So sodium has a +1 charge. Fluoride has a -1 charge. And if we put them together in a 1-to-1 ratio, the charges add to 0. That makes a compound. We always put the metal first, the nonmetal second, cations before anions. And then even though the charges are still present, we hide them. Barium has a +2 charge, so we can't just put 1 barium ion with a fluorine because we would end up with some overall charge. So we're going to need 2 fluorides to balance that barium ion. So 1 barium ion has a charge, overall charge, when you add all the protons and electrons together, a +2. And then 2 fluorides match that. Because there's 1 barium to every 2 fluorides, we could write it like this, but if there's a 1, we let the 1 be implied. Like when we write the formula for the molecule water, we say H2O. We could say H2O1 because that's the ratio, 2 hydrogens to 1 oxygen, that is every molecule of water. But we don't put this superscript or subscript 1 there. It's implied. Okay, this is covalent because these are both nonmetals. So for barium fluoride, we put the cation before the anion, and if there's more than 1 of a particular monatomic ion, we show that with a subscript. Here we have aluminum. Aluminum has a +3 charge to make it isoelectronic with neon. Fluoride is -1, so we're going to need 3 fluorides. 1 formula unit, the unit for the formula for aluminum fluoride, has 4 ions in it. 1 aluminum, 3 fluorides. Okay, so we could do the same thing here. Sodium with sulfide. There's 2 sulfides -2, sodium's +1. I'm going to need 2 sodiums. to balance that -2 charge. And I always put the positive one first. So I put the subscript after the sodium before the sulfide. And when we make these ionic compounds, we don't show the charges. If we had the free ions, we would show the charges. Barium sulfide, well, barium's +2, sulfide's -2. They just come together in a 1-to-1 ratio. For aluminum and sulfide, I need the lowest common multiple of 3 and 2, and that is 6. So my goal is to have +6 for the cations and -6 for the anions. What that means is I need 2 aluminum ions and 3 sulfides, because every sulfide has 2 extra electrons. And to get to -6, I need 3 of those. And then when we put it together, 2 aluminum ions and 3 sulfide ions, the 2 goes here, subscript, and the 3 goes here, subscript. Some of you may have heard a thing called drop and swap or swap and drop. Don't do that. It can lead you astray. If you don't know what I'm talking about, good. I am appreciating your innocence. Okay, and then we have nitride. Nitrogen can gain 3 electrons. We're going to need 3 sodium ions to balance that -3 charge. With barium, we have that 2-3 situation. Shoot for 6, the lowest common multiple. And aluminum nitride comes together in a 1-to-1 ratio because +3 and -3 add to 0. Why does it need to be 0? To be a compound. Why is it an ionic compound? Because it's made from ions. Okay, so both in the name and the formula, we always put the cation first. So here I go. I want to name this first one. It was sodium ion and fluoride. Ion. We're going to drop both the ions and then stick them together. So the name for the first one is sodium fluoride. What happens if there's a subscript? And the answer is nothing changes. So here we have barium and fluoride. Barium ion becomes barium. Fluoride ion becomes fluoride. We don't say anything about the 2 because anybody with a periodic table knows that barium has a +2 charge based on its position, and that fluoride has a -1 charge based on its position. So barium fluoride. Alrighty, so transition metals, that's this group here. The thing about these is they have a long ways to go to be isoelectronic with a noble gas. Oops. So iron, for example, number 26, to get back to a noble gas, it would have to lose, to be isoelectronic with argon, it would have to lose 8 electrons. And a charge that high is not stable, so it doesn't do that. Iron can be iron the atom, or there's 2 charge choices possible, iron 2 and iron 3. Why 2 and 3? There's reasons we'll talk about later in the semester, but for now you just need to know, for transition metals, when they make ions, there's typically more than 1 charge choice. But like everything, there are exceptions. So silver, when silver metal becomes silver ion, has a +1 charge, always. That's the only possibility for silver. Zinc and cadmium, +2. And then things in group 3 would of course have a +3 charge. So if you want to remember these exceptions, these things that don't have variable charge, even though they're in the unknown zone where there's other charge possibilities, you might think of the stair steps. And then these could only be +3 because of their column. They're representative or main group elements in column 3. Okay, but for the other ones, there are possibilities. And I will go into detail on the video. So I'm not going to spend the time now to spend a lot of time on this. But just understand that, that for iron, there's 2 possibilities. One is +2, and one is +3. And in our class, there are 7 of those that we just have to know have 2 possibilities, and they are given on that list I showed you earlier. Let me show you again real quick. Let's see. Okay, so on this list, it talks about how copper can be +1 or +2. Mercury can be +1 or +2. Chromium, cobalt, and iron, charge choices are +2 and 3. And then for tin and lead, the charge choices are +2 and 4. And I have a periodic table that I've made. I will upload it and attach it just so you can see it's colored in a way that might be useful when you take your quizzes and tests, especially at the beginning when you're first learning how to do this. What I've done is I've color coded it. There's a key down there in the lower left. And just reminded myself about main group elements, how their charges would change, and then about the 7 exceptions, ones that have 2. I just want to point out that everything else in here, even though the periodic table that I will post right after class that I've colored on, you could make your own or you can print mine, whatever you want to do. Even though it shows 7 exceptions where there's 2 charge choices, understand that things in the unknown zone have more than 1 charge choice. For manganese, it's not, I haven't given it choices, but there's 5 choices. Vanadium, 5 choices. So you just need to know that there's more than 1 possibility, except for silver, cadmium, and zinc. And so for that reason, when we make compounds with transition metal ions, if there's more than 1 charge choice possible, which is true for everything except silver, cadmium, and zinc, we have to state which one we're talking about. So here, this isn't copper, this is called copper 1. And we write the 1 in parentheses, no space there, and with Roman numerals. So copper 1 and fluoride make this compound that is called copper 1 space fluoride.
So we can't see what you're writing.
Oh, that's not helping, sorry. See, if you didn't talk to me, I'd be talking to myself, looking at a page and nobody can see. Okay, so my point is just, for elements in the unknown zone, you have to state the charge, and that's what's happening here. This is stating the charge on that ion. It's not saying anything about how many, just like we did on the previous screen. So here we have iron 2. Because iron 3 is a possibility, we need to know which one we're talking about. So iron 2 ion is going to need 2 fluorides to make the compound. And we call it iron 2, that's the cation, space, fluoride, that's the anion. That's the name, iron 2 fluoride. What does that 2 mean? It means the charge is +2. It has nothing to do with the 2 besides the fluoride directly. Okay, and there is also the possibility of iron 3 fluoride. Iron with a +3 charge needs 3 -1s. Alrighty, questions? So this is contained in the video. You can fast forward to the part where you see this table, and then you can do the table yourself and then compare to what I say. Let's see. So you need to look at the periodic table and know from main group elements what the charges are, and then how to put them together so the charges add to 0. And then sometimes you're going to have to go the other direction. So somebody's giving you a formula and you're going to write the name. When that happens, you're going to have to stop and ask yourself, is this a main group metal or is this a transition metal? If it's a main group metal like calcium, we just say calcium chloride. So it's metal plus nonmetal. That makes it ionic. Calcium ion is the cation, chloride ion is the anion. It took 2 chlorides to balance that calcium charge. But for this one, which is also ionic, it starts with a metal, is copper is in the unknown zone, and so I have to figure out which copper it is. Well, I know chloride is a -1, and I see that there's 2 of them. So 1 copper ion has to balance that -2 charge. This must be copper 2. Okay, so this one is a little unusual. Here we have 10, and this is 10 on the periodic table. And 10 is not a transition metal, but tin and lead both have 2 charge choices. They're on the list that is in the nomenclature packet that is in your module this week. So I have to recognize that tin, oops, that's lead, that tin and lead have 2 charge choices, and they are 2 and 4. So which 10 is this? Well, let me look at the anion, oxide. Oxide has a -2 charge. It's in group 6. It needs to gain 2 electrons to be like something in group 8. And there's 2 oxides, which means -4. It must be 10,4 oxide, because 10,4 can balance that charge. So that's an exception because it's a main group metal, but it's one of 2 that have variable charge. Okay, and then here's another exception for a different reason. Here I have silver oxide. Even though silver is a transition element, it's one of 3 that doesn't have variable charge. And so we just say silver oxide. We don't say silver 1, even though the charge on it is +1, because silver can only be +1. Zinc and cadmium can only be +2. These are 3 exceptions because they're transition metals that aren't variable. Questions? Okay, so that's all I have for you, but I do want to offer some advice, and you'll take it or you'll leave it, but you're the ones that showed up, so I think you'll probably take it. Good for you for being here, and good for you for diving in. You need to become familiar with your periodic table and maybe color one like the one I'm going to post in a minute. You need to be able to put these together to form a compound. So that would be maybe taking the names and writing the formulas. And then you also have to be able to see a formula and write the name. And we all have a favorite direction. So you need to practice both directions, and whichever direction is more difficult, you need to practice it more. The next thing is you need to practice nomenclature every day. Today, I have just started you on ionic nomenclature, and it does get a little more complicated. Maybe I'll do that tomorrow. And then next week we'll have covalent, and then all these things start mixing in our brain. So the sooner we make flashcards and iron out some concepts, the sooner that you do maybe these grids and check your work. And when you have questions, see what your questions are and get your questions answered, the better off you will be. Okay, so here I am, week 5, ions and ionic compounds. Here's a nomenclature packet. It's like 22 pages. Don't worry, that's 2 weeks worth of nomenclature. But the first 6 or 7 or 8 pages, there's a grid, there's a key. There's a grid, there's a key. You need to do those. And I recommend that you don't do them all at one time. that you do a little bit every day. In fact, if anybody has practiced an instrument, you're probably familiar with this idea. If you practice 30 minutes a day, that is so much better for you than practicing 3 hours in one day. Like if every week you break out your 3 hours of practice into 6 days, you retain a lot more. And the same is true with nomenclature. It's like building a muscle. You know, do you go running every day, or do you just wait for the marathon and run all your miles on that day? That's not a good idea. So it's real important that you do more nomenclature than you think you should. Okay, that's all I got. Any questions?